We now move on to discuss another important concept in LTL, and in any logic for that matter, namely formula equivalence. We say that two formulas, phi and psi, are equivalent, written phi equivalent psi, if they are satisfied by exactly the same state labelings and infinite sequences of states. More precisely, given any labeling n and any infinite sequence of states pi, we have that pi satisfies phi with respect to labeling L, if and only if pi satisfies psi with respect to labeling L. This is the same as saying the following two facts. That on the one hand, pi satisfies phi implies pi satisfies psi, and on the other hand, pi satisfies psi implies pi satisfies phi, all with respect to the labeling L. As you can see, equivalent means that they are semantically the same. One is satisfied by an infinite sequence whenever the other is satisfied, and vice versa. And it is easy to see that this applies to LTSs too, not only to infinite sequences. In that for two equivalent formulas, phi and psi, we have that they are satisfied by the same LTSs in the same states. For any LTS M and any state of it, we have that M in S satisfies phi if and only if M in S satisfies psi. Just to make sure that you have grasped the concepts of satisfaction and formula equivalence, please prove this as a homework exercise. Namely, prove that any two equivalent formulas, as we defined them above, are also satisfied by the same LTSs in the same states. Here are some formula equivalences which hold in general, no matter what the particular participating formulas phi and psi are. First, the so-called propositional tautologies, which are true by the semantics of propositional connectives and simple logic. Things like not phi and psi is equivalent to not phi or not psi, and dually, not phi or psi is equivalent to not phi and not psi. These are incidentally known as De Morgan's laws, but there are many others. Can you think of others? Then there are the duality laws, involving negation and temporal connectives. Not next phi is equivalent to next not phi. Not always phi is equivalent to eventually not phi. And not eventually phi is equivalent to always not phi. This can be proved from the semantics of the involved connectives, but it's always worth pausing for a second to try to grasp intuitively why they are true. For example, saying that phi is not true at the next moment is really the same as saying that at the next moment phi is not true. Saying that phi is not always true is the same as saying that sometimes phi is not true, which in our temporal setting means that eventually we'll reach a point where phi is not true. In other words, eventually not phi. Then we have the distributive laws, saying that phi and psi are always true is the same as saying that phi is always true and psi is always true. Similarly, eventually phi or psi is equivalent to eventually phi or eventually psi. And perhaps a bit harder to see why. Next phi until psi is equivalent to next phi until next psi. These are called distributive laws because they allow one connective to distribute over another. Always distributes over and, eventually distributes over or, and next distributes over until. Note that, on the other hand, always does not distribute over or, and also eventually does not distribute over and. So these are counterexamples where equivalence fails in general. Just to keep in mind that not everything distributes over everything. Then there are the Inter-Definability Laws, which show that some connectives are definable from others. Eventually is equivalent to not always not, and similarly, always is equivalent to not eventually not. Also, eventually is equivalent to true until. So let's see why this, what's the intuition behind these laws. Something being eventually true means that it is not always false. In other words, it is not always not true. So this explains this law. Similarly, something being always true means that it is not the case that eventually it will be false. Now, this last law here shows that eventually can be defined from until. First, let's clarify what this formula true is. This is just an abbreviation for P implies P for some atom P. So it's just a formula that is going to be unconditionally true. Now, to see why this equivalence holds, remember the semantics of until. The right-hand side of the formula, here phi, is supposed to hold at some point. In other words, to eventually hold. And until then, the formula on the left, here, true, is supposed to hold. Which is the case here because true holds everywhere. So true until phi really means the same as eventually phi. Moving on, there are also the idempotency laws, stating that some connectives are semantically idempotent, meaning that applying them twice, as here, 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 or here, is the same as applying them once. Has the same effect from a semantic point of view. For example, what does it mean that eventually phi holds? Well, it means that there is a point in the future such that there is another point further up in the future such that phi holds. So we just applied twice the semantics of eventually. But this is the same as simply saying that there is a point in the future where phi holds. This is why we might as well have said eventually phi instead of eventually phi. This is why the two are equivalent. And similar equivalences hold for always and until. Then there are the absorption laws, called like this because they show how one of the connectives can be absorbed by the others in specific contexts. Here, for example, the law says that always eventually always phi is equivalent to eventually always phi. So the first always is absorbed. Why does this law hold? Well, think about what eventually always eventually phi says. It says that for all points in the future, there exists a further point up in the future from which phi will always hold. But we might as well settle for the first such point in the future. So we might as well say there exists a point in the future from which phi will always hold. In other words, eventually always phi holds. And a similar absorption law holds for eventually always eventually, where the first eventually disappears. It is absorbed. Finally, and perhaps most importantly, we have the expansion laws. Eventually phi is equivalent to phi or next eventually phi. Why is that? Well, if we look at the semantics of eventually, we see that eventually phi really means that phi either holds right now or at some point strictly in the future. So either phi holds or next eventually phi holds. Similarly, always phi means that phi holds both now and strictly always in the future. In other words, always phi is equivalent to phi and next always phi. As for until, phi until psi means that psi will hold at some point in the future and phi will continuously hold in the meantime. This is just the semantics of until. So I have two cases. Either phi holds right now and we are done, or phi must hold right now and phi until psi must hold next. Note that the ideas behind the expansion laws for eventually and until are similar. There is some potentiality of something holding at some point, some promise of something holding at some point, and we split in two cases. Either this happens now or things are postponed till next time.